Tutorial sheet 3, question 3. This one is relating to an Armstrong modulator, and it's quite different to the other questions that you'll see because there are no specific answers. This is more of a design question of how you go about designing one of these systems. So what I've done, I've drawn the basic layout of an Armstrong modulator, including the multipliers and the mixers that you need. What we're given in the question is that we need the output parameters have a carrier frequency of 97 that should be megahertz, and a maximum frequency deviation of 75 kilohertz. And you'll notice on the question it says starting with an oscillator working near 500 kilohertz. So it doesn't have to be 500 kilohertz, it can be anything around there. And also that you have a frequency deviation, initial frequency deviation not exceeding 30 hertz. So there are an infinite number of answers to this, and also you're not given what the second oscillator is. So it's about how you design this structure. So what I'm going to go through is just the basic fundamentals that you need to solve this, and then you need to prove to yourself that you can actually design a system like this. So what I'm going to do is I'm going to track both the frequency deviation and the carrier frequency as we move through the stages. So I'm going to have a box for delta F and then carrier frequency as we work through the system. So at the moment we've got a delta F1 at the beginning, which, as I say, is something around 30 hertz, and a initial carrier frequency F1. So as we pass through to the next part of the system, this is a frequency multiplier. So in other words, what we're doing is we're multiplying everything by N1 here, so that the output of this is going to be N1 delta F1 and N1 F1. So both the frequency deviation and the carrier frequency are going to increase by that factor N1. And then we go into a mixer stage. And the mixer stage doesn't affect the frequency deviation, but it does affect the carrier frequency. And so what we're going to do, we're going to assume that F2 is larger than N1 F1, so that the output of this stage is going to be the difference between this frequency and this frequency. So at this point here we're going to have F2 minus N1 F1, and the assumption is that F2 is greater than N1 F1. Doesn't have to be, but that's the assumption we're making in that particular situation there. But this mixing process does not change the frequency deviation, so that frequency deviation is still N1 delta F1. And then we go through to another stage of multiplication. So again we multiply by N2 to give us our final frequency deviation, N1 N2 delta F1, and N2 into F2 minus N1 F1. And we know at this point what the answer should be because we're given that here. So that has to be equal to 75 kilohertz, and that has to be equal to 97 megahertz. So we've got 1, 2, 3 unknowns, and we've only got 2 equations, so this is why there's an infinite number of solutions. So it's all about how you design and trade off the values of N1, N2 and F2, and you can use those equations and put in whatever numbers you wish to get this answer.